Hello, and welcome again to FlippedHarber for Physics. In this video, we'll be going over the practice problems, page 48, numbers 25 through 28. In number 25, it says the graph in figure 222 describes the motion of a cruise ship during its voyage through calm waters. The positive D direction is defined to be south. We're asked to determine what is the ship's average speed and what is its average velocity. Now let's take a look at the graph first. It's a little odd, but totally legal, to make the positive D direction south. That would make the negative direction north. I just want to make note of this because it is kind of unusual. So in order to find the ship's average speed, we're going to need to talk about how far it goes in a certain amount of time. Now we're going to have to do some estimating here because there aren't any grid lines on our graph. So I'll help out by drawing a vertical and a horizontal line. We see that the ship covers about 1.3 meters in 4 seconds. So we can use that to make a calculation for speed. We'll just say that speed is equal to 1.3 meters divided by those 4 seconds. And we get an answer of 0.33 meters per second. Now that's great for speed, but what about the average velocity? In order to turn this from a speed into a velocity, we need to tack on a direction. Well, remember how the positive D direction was south? Well, that means that this ship is actually going north. So as soon as we tack that direction on, we have a velocity, 0.33 meters per second north. Now in a situation like this, you really don't need to show the calculation twice. I just put it on there because it was easy to copy and paste. Taking a look at number 26, it says describe in words the motion of the cruise ship in the previous problem. So really we've done this, we just need to make it look like a sentence. We'll simply say that the ship is moving north at 0.33 meters per second. Taking a look at 27, the graph in figure 223 represents the motion of a bicycle. Determine the bicycle's average speed and average velocity and describe its motion in words. So again, we're given a position time graph. A couple small changes. Our position is in kilometers. Our time is in minutes. Really doesn't change much in terms of our calculation though. Looking at the beginning of this position time graph, we see that the bike starts out at the origin, and then when we look at the end of the position time graph, the bike has gone 20 kilometers in 30 minutes. So we're going to use that in order to determine our speed. We'll take the 20 kilometers, divide by the 30 minutes, and get a speed of 0.67 kilometers per minute. Now, if we're going to answer the question, what's the average velocity, we need to figure out some sort of direction for this. They did not tell us anything about the positive D direction like they did in the previous problem. So if we don't really know what direction it's going, how do we give a direction? Well, we can always give something in a very vague term, something like away from the origin. I know it sounds goofy, but it gets that direction covered. So we say that the bicycle's velocity is 0.67 kilometers per minute away from the origin. We were able to give a speed and a direction, so that's velocity. So we'll just write that as a sentence. The bicycle is traveling at 0.67 kilometers per minute away from the origin. Alright, let's move on to number 28. When Marilyn takes her pet dog for a walk, the dog walks at a very consistent pace of 0.55 meters per second. We're told to draw a motion diagram and position time graph to represent Marilyn's dog walking the 19.8 meter distance from in front of her house to the nearest fire hydrant. So I need a number line, and it turns out that the two numbers that they give us, the 0.55 meters per second and the 19.8 meter distance, work together very, very well. So I'm going to go ahead and start my number line at 0, end it at 19.8 perfectly. If I wasn't exactly sure, I could always just round that up to 20, but it does work out perfectly. We see the dog, because this is a motion diagram, not a particle model. at t=0. Now, to draw a dog for every single second would be a little too cumbersome. So I've broken it up so that we're going to see a picture of the dog every 6 seconds. Now, you don't need to label this second picture in your homework. I'm just doing this for our discussion here. But you're going to see a dog for every 6 seconds of motion. So it turns out that it takes 36 seconds for the dog to walk to that nearest fire hydrant. So we see a dog for t=0, t=6, 12, 18, so on, all the way up to the 36 seconds to go the 19.8 meters. Okay, so now what about that position time graph? Well, I've got my axes, I've got everything labeled out nicely. Notice I broke it up in a more general position. Instead of ending at a perfect 19.8, it's actually ending at a 20. Now my time does work out well, so I went ahead and labeled it by every 6 seconds. Each box is 2 seconds though. So I'm going to draw a green line. Remember, this is a position time graph, so it should be in green, that goes from the origin and it ends just shy of that 20-meter line at 36 seconds. Okay, so that's it. I hope you've learned a lot. I hope you're enjoying this process. I'll see you in class, and I'll see you online.